Alright, number 88 says you got a student that's standing on a bathroom scale. So here's my student on a bathroom scale. And the scale reads 836, so that's their weight. That's nice. They're telling me right off that the scale is reading 836 newtons. And so as they go up, they find that the scale reads 936. Ooh, baby. So this is definitely bigger than that. So they have to be accelerating in this direction. They have to be. Right? So I can actually simplify this person. This is the net force. The net force of this person is 100 newtons. Right? Because if you pull down 836, you put up 936, the 936 definitely wins, and it's 100 newtons. And it says find the acceleration. So if you're going to use F equals ma, remember to use the net force. And we just found the net force is 100. And the mass of the person. Here's the person's weight. So in order to find their mass, you got to divide by 9.8. Because the force is 836, and the acceleration is 9.8. So you got to take 836, divide by 9.8. And you get 85.3 as their mass. So 85.3 is the person's mass. Stick it in there, and then you take 100 divided by that answer, and you get a 1.17 as the acceleration. Very good. That's part A. Part B says, 88, part B. As the elevator approaches the 74th floor, the scale reading drops to 782. So we're going to start this over, this whole process. Person on a scale, still read, gravity's still going to be the same thing, 836 newtons. Scale pushes up at them a little tiny amount this time, and it's 782. Right? So you subtract those, 836 minus 782, and you get 54. So F equals ma. The net force, you subtract the two, because I guess I'll say positive is up, so 782 minus 836. The mass I found before was 85.3 times the acceleration, like this. So 782 minus 836 divide by 85.3, and you get negative 0.633 meters per second squared. So I guess I would go like this. Acceleration equals 0.633 meters per second squared down. Because you have to give a direction to it. I guess you could say you could go with the negative. The negative seems pretty, like you could say, if you have your little legend over here. So, part C says, using results for parts A and B, explain which change in velocity, starting or stopping, takes a longer time. Okay, so I think this is when it was starting. Yeah, so this is when it starts moving. And part B was, it says, as the elevator, this is when it stops. Well, it looks like it starts moving at quite a clip, so every second that goes by, it gets 1.17 meters per second faster. And then here, it's only getting 0.6 meters per second faster every second. So when it says which change in velocity takes a longer time, it's definitely stopping. Stopping takes a longer time because it is decelerating at 0.633 meters per second squared. As as opposed to starting at 1.17 meters per second squared. So it's almost like starting twice as fast, then it stops.